Today we're going to be talking about a new topic. We're going to be starting chapter 15 in our course, which is on antiderivatives. You might remember from other arithmetic type applications that most math operations have a way to be undone. For example, you learned algebra and you learned that if you want to undo an addition, you subtract. If you want to undo a multiplication, you divide. It turns out that differentiation also has an inverse process like this, and it's called antidifferentiation. It's also called integrating. If you think of differentiating as taking things apart, then integrating is putting them back together again. So what we're going to do today is we're going to introduce antidifferentiation. It's pretty much just reversing the processes you used for differentiation. I will kind of caution you that there are lots of patterns involved, but just like I gave you a derivative cheat sheet, you're going to have an anti-differentiation cheat sheet, and I'll show you that as we move along. It's important to realize that all of the material that I am using for these online lectures exists in your My Math Lab course, and it's typically in the notes and videos section. So if you go to our course, you look at chapter 15, okay, in the notes and videos section, you'll see the things I'm using, whether it's a PowerPoint, whether it's my class notes, or whether it's, handouts that I give you, in class, or in this case that I'm using online. Okay, so let's get started. I'm going to start with my class notes. And again, what I'll do is I'll share my screen with you. Okay, I'm not sure what happened. Okay, can everybody see the screen? Can everybody see the screen? Can you type in the chat, please? Can you see the screen? Again, I lost the WebEx meeting. I'm trying to find it. Okay. I'm going to stop sharing my, and I can't see the chat or anything. Okay, everybody could see that. All right. For some strange reason, I wasn't able to see you guys, so I wasn't sure if you could see me. All right, I'll try to share that again, and we'll walk through it, and then I'll stop sharing to come back and ask questions, okay? I'm going to try to just share the application this time. Let me. Okay. All right. So what I have here are my class notes. And again, let's see where that is. Nope, wrong thing again. Sorry. Again, I have a new interface, so I'm playing around a bit. Sorry. Okay, try again. I think I was better off with just sharing my screen, so let me do that again. All right, so now here's my class notes. And again, what I'm talking about in anti-differentiation is, suppose we have marginal function, like a marginal cost or a marginal profit function. We know the rate at which a quantity is changing, And suppose we want to build from that marginal function a total function, like a total cost function or a total profit function. Okay, that would require that we take the rate function and anti-differentiate it to get the total function back again. Okay, so our marginal function is a derivative, and if we want to get the original function back again, we have to anti-differentiate. Okay, here's the relationship right here. If f prime of x, big F prime of x, in other words, we took a derivative, is little f of x, then to get this big function back again, we have to anti-differentiate that rate function. Okay, here's a couple of simple examples. Let's take a look. Okay, so if f of x is 10x and we differentiate it, we're going to get 10. So f of x equals 10x, again, is the antiderivative of this. In other words, here's the derivative. To get back to the original function, we would anti-differentiate. Okay. Likewise, if big F of x is x squared, then when we differentiate it, we get 2x. If we reverse the process and we anti-differentiate 2x, we should get the x squared back again. Okay, so again, how do you find the antiderivative of a function? Well, this can be difficult depending on how complicated the function is, and what we're going to spend the rest of the semester doing is learning how to anti-differentiate various types of functions. There are lots of general rules. Okay, and again, I'll show you one of these sheets that I've got here. Okay, this is something that is in your course under chapter 15, class notes and videos, and it's under the handout section. It says integration summary. Okay, so this is like your derivative cheat sheet, but it's for antiderivatives, which are also called integrals or integration problems. Okay, so again, don't worry about the notation or anything. I'm just showing you this document so you know that it's in our class if you need to refer to it. Again, go into course notes and videos, look for chapter 15, because that's where this material is, and this is under handouts. Okay, well, to go back to our question, how do you anti-differentiate something? Okay, so here are some notes I made up in advance, and I'll share these along with the video when I upload it to our class. Let's say we have an f of x function, and let's say it's x cubed plus 4. Okay, we want to basically see what happens when we differentiate this, and then we want to try to come up with steps that reverse the process. So what I'm showing you here is what anti-differentiation actually is, and I'm using a simple example with the power rule. Okay, so here's our starting function. If I want to differentiate it, what am I going to do? I'm going to take this original exponent 3, and I'm going to multiply the x term by it. Then I'm going to subtract 1 from the exponent. Everybody remember that? Basically, I have x cubed. I'm going to basically bring the 3 down in front and then subtract 1 from the 3 to make it 2. Okay. The derivative of the 4 is a 0, but the derivative of any constant will be 0. So it really doesn't matter what this constant is. We're going to see later when we reverse the process what this situation creates, okay? But for now, don't worry about the constant. Focus on the x term. Okay, so everybody, I'm sure, will agree that the derivative of f of x is 3x squared. Okay? Now, what we want to do now is we want to reverse the steps of differentiation. So how do we do that? We're going to go backwards up the process. So we're going to handle step 2 first, and we're going to reverse all the operations in it. Step 2 was subtract 1 from the exponent, okay? So our first step to try to get f of x back again is to add 1 to the exponent, okay? So now this would be 3x squared plus 1, okay? Then, backing up one more step, I would take that exponent and multiply the x term with it. But here I'm going to take that new exponent and divide the x term by it. So what you want to notice about the process is you're going backwards in the steps and you're also reversing the operations in the steps. Okay, that's how you undo derivative with a power rule. So here's what happened when we actually applied it. We started with 3x squared, and the first step was add 1 to the exponent. You can see that up here. I have 2 plus 1 in the exponent. Oops, undo. Trying to highlight it, but it's not working. There you go. There's the adding 1 to the exponent. And again, I have to do the same thing down here. Right? I'm going to divide by that new exponent. Well, what happens then? Okay, my 3x squared becomes 3x to the 2 plus 1, or 3x cubed, and the 2 plus 1 on the bottom becomes a 3. You'll notice the 3 on top and the 3 on the bottom cancel out, divide out, and I'm left with x cubed. That was part of my original f of x. So what's this plus c? Well, plus c is a constant that we have to add to our antiderivative, okay, because it represents whatever this constant could have been, right? It happened to be a 4, but it could have been a -10, it could have been a 1, it could have been anything. And I really can't tell from the antiderivative what to put there. So I'm going to put a general constant, okay? And basically, if I need to find out what the constant was, I'm going to need more information about f of x. For example, I might need to know that when x is 0, f of x is 4, okay? In which case, I can plug that information into my antiderivative and figure out what c is, okay? But for now, whenever you do an antiderivative, you're going to add a plus c, and that's going to represent any constant that may have been part of your original function, okay? So let me stop for now sharing, okay? And I'm going to go back, and I'm going to basically ask anybody have any questions. Let's see if I can bring up the chat from here. Any questions? Okay, any questions so far? Can you please just give me a shout out, yes or no, just so I'm sure everybody's following? Okay, anybody else on? Good. All righty. Well, let's go back to my notes, and I'll show you exactly what I'm talking about here. Okay, so here I have the first thing to note about my antiderivative is that all of these three functions, f of x equals x squared, g of x equals x squared plus 1, h of x equals x squared minus 5, all of these, if I were to differentiate them, would have a derivative of 2x. Okay? Again, when you take a derivative, you effectively lose the constant. Okay? And so when you take the antiderivative of 2x, you don't know what the constant should have been. Okay? So we're adding this arbitrary number c to the antiderivative. It's called an integration constant. Okay? Sometimes they're going to ask you to determine what that is, but they're going to have to give you some additional information about your original function in order to do so. Okay? So for example, with f of x, they'd have to tell you when x is 0, f of x is 0. When in g of x, when x is 0, g of x is 1. In h of x, when x is 0, h of x is -5. Once they tell you that piece of information, then you can figure out exactly what c should be. Okay. But for now, that's what the integration constant is. It's a placeholder for whatever the constant was in your original function. Okay, let's take a look at some notation for antiderivatives. Again, this is an introductory section, so a lot of what we're going to be talking about today is definitions and notation and some rules. And what I'm going to do in between each segment is kind of give you the opportunity to play with the concepts, okay? So don't worry, we're going to take our time. So here is some notation for antiderivatives, okay? This big S-shaped symbol, which you'll notice is as big as the f of x, right, is called an integral sign or an antiderivative sign. Most people will call it an integral sign. The f of x that we're integrating, okay, is also going to have this dx differential with it. And what the dx is telling you is f of x is your function that you want to find the antiderivative of. Dx is telling you you're integrating with respect to x. In other words, x is the thing you're going to start playing with the exponents of and all of that, okay? This is important when you've got different variables in an integral. Don't worry, it'll always be clear in this course what variable you're integrating with respect to, okay? But that's what that notation means, okay? This whole thing that comes after the integral sign, okay, is called the integrand, okay? And all that means is it's the thing we're trying to find the antiderivative of. This is the format of an answer, okay? This is what the antiderivative looks like once we do the antiderivative process. Okay, we're going to get a function, and then we're going to add this plus c, which is the integration constant. Okay, any antiderivative like this that has an integration constant added to it is called an indefinite integral. Okay, and we'll see what definite integrals are later on. Okay, so we've introduced 3 new terms to describe this. Okay, I said this is in general called an integral. It's also called antidifferentiation or an antiderivative, okay? And it can also be referred to as an indefinite integral when you see the plus c over here, okay? So again, just get comfortable with the different notation and with the different vocabulary. And remember, you have these class notes in my math lab, okay? So you can always go back and review them. Okay, so let's take a look at some uses of the notation. Okay, so here is the integral or the antiderivative of 2x dx. Okay, remember my exponent on x is a 1. So my first step says add 1 to the exponent. Now my exponent's a 2. Then the second step is divide both by 2. The 2's cancel out and I get x squared, and then I put plus c here. Okay. I think it might be a good idea for you to try some of these before we get too involved in rules, okay? The only rule I'm going to show you is this one, which is the power rule that we just did a couple of times. Okay, so if you've got an exponent, as long as it's not -1, we'll get to that in a minute, okay? If you have some x raised to some power that's not -1, then all you have to do is, here's our steps. Add 1 to the exponent, divide by the new exponent. Those are the same steps that we had earlier on in the video, right? And then we're going to add a constant to it. Here's the example I showed you, only this one does not have, okay, any constant on it, okay, to start with. But here is the integral of x cubed dx. We're going to take the x, we're going to add 1 to the 3, and then we're going to put the new exponent in the denominator, okay? Remember to add the constant of integration because, again, we didn't know that this was a 0. It could have been a 1. It could have been a -3, okay? So put a plus c to placehold for the constant. And then, again, remember to basically rewrite this as x to the 4th over 4 plus c. Okay, Sometimes when you're doing these, okay, it is important to, like we've done with differentiation all semester, start out by rewriting any x's in the denominator, like 1 over x squared, write it as x to the minus 2, and rewrite a square root as x to the 1/2, okay? It's easier that way. It's much easier that way, okay? So again, what I'm going to try to do, okay, I'll ask if there are any questions, okay, and then we'll see if we can try one, maybe on the board. I want to see if the board projection works with this new version of WebEx I have, okay? All right, so what if there was no constant? That's a good question, Nancy. Basically, no constant means it was 0, okay? So 0 is a number just like 4 or -5, right? So again, this constant plus c, okay, is holding the place for whatever that number was, whether it was 0, a negative number, a positive number, or whatever. Okay, so any questions so far? How are we doing? Any questions so far? Okay. Can the rest of you chime in? I want to just make sure we're all together, and then we'll have you try a few, okay? Okay, I'm going to go back to just sharing my video. So I'm going to stop sharing my notes for a minute. Okay, so hopefully you can all see me now, and hopefully you can see the board behind me. So I'm going to put up a few examples and we'll see about trying those, okay? Just give me a minute and I'll put them up. These are you tries, okay? So you try. Okay, you find the antiderivatives. Okay, everybody able to see that? Here's the second one. Um, okay, try those two. Okay, can everybody see the board? We're good? Okay, try to find them. Okay, we'll take a minute and then I'll ask you to try to type what you got into the chat. Okay. My screen froze. Okay. Okay, can everyone else see the screen? Okay, Yesenia can see it. Can I please get a check-in from everybody? Can you see my screen? Okay. Yeah, refreshing is a great idea. If you are ever in one of these meetings and it locks up, try refreshing your screen. Remember what we're doing. We're adding 1 to the exponent, dividing by the new exponent, and then adding a c. Again, as soon as you have an answer, just type it into the chat. You can use calculator notation for the exponents, like use the up arrow, the caret, for an exponent. Okay, I have one answer, x for number 1, x to the 5th plus c. I'm going to wait for everybody else to give it a shot. Okay, if you're done with the first one, type your answer in. If you're, you can start working on the second one. Okay. If you're stuck, type a question in the chat, okay? Okay, I think I'm getting some answers for number 2. Okay, another half a minute and then we'll work on them together. Okay, let's take a look at these two and walk through the process. Let's do the first one over here. Okay, according to the process for using the power rule, which again, I'm going to use on a polynomial, just like I would use the power rule for differentiation on a polynomial. I'm going to start out by taking this term and I'm going to add 1 to the exponent. So I now have a 4 plus 1 up there. Then I'm going to divide by the new exponent. And then put a c to represent whatever constant was here to start with. Now in my original function, okay, I just have a 0. There's no constant. But 0 is a number, just like anything else. Okay, so let's take a look, right? If I simplify this, I'm going to get 5. 4 plus 1 is 5. So 5x to the 5th over 5. And again, you can see these cancel out. So my final answer is x to the 5th plus c. Which again, the majority of you who typed in the chat did get that. Let's take a look at the second one. The second one is very similar, okay? Just slightly different numbers. With this one, I'm going to add 1 to my exponent. Okay, and then I'm going to divide by the new exponent. And then put the constant of integration afterwards. Simplifying this up a little, this is going to give me 4 times x to the 3 plus 1 is 4 over 4. these are going to cancel out. So I'm going to get x to the 4th plus c. Okay. Again, from looking at your chat, the majority of you were good with that. You were able to get those answers. But let me stop and ask, does anybody have any questions? Okay, any questions at all? Okay, again, I'd appreciate it if you could just, give me a shout out just so I know. Okay. Now, again, I set these up so that you'll notice the original coefficient and the constant that we got on in the denominator canceled out nice and neatly, but that doesn't always happen. Okay. Let me show you an example where, again, you're starting out with a constant, okay? And it's not going to cancel out evenly. It's okay. It's just a number, okay? So just like these happen to cancel out, sometimes they don't, right? Let's take a look at an example like that. All right, suppose I have an antiderivative of okay, 2x cubed dx. Okay, I'm going to walk through this and just show you how it would work. Just like when you're differentiating, you want to make sure you just pull through the constant. Don't do anything with it while you're doing the antiderivative. Okay, just pull it through and focus on the part of the integrand that has the variable in it. I'm going to pull the 2 out over here, and I'm going to do my business with the power rule here. I'm going to add 1 to my exponent. Okay, and then I'm going to divide by the new exponent. Okay, then add my constant of integration. Right, and then the rest of it is just pretty much arithmetic and algebra. Okay, so this is 2, 3 plus 1 is 4, and then I have a 3 plus 1 on the bottom here. Okay. Now again, this can be simplified further, right? I can divide a 2 out of the numerator and a 2 out of the denominator, so let me do that. Okay, 2 goes into 2 once, which I don't need to write. Or I could put 1 like that. And then 2 goes into 4 twice. So basically, I could say 1/2 x to the 4th plus c. Okay, you could also write it as x to the 4 over 2 plus c. So you can see sometimes you wind up with a different coefficient in the front. It's not 1. Now you might say, how do we know this is right? Well, again, you want to see that you get this back again if I were to differentiate it. So let me go over here. And I'm going to differentiate this piece in here, which is 1/2 x to the 4th plus c. C is a constant, right? So I know the derivative of it is going to be 0 no matter what its value is. Okay, so we don't have to worry about that so much. Okay, but let's use the power rule for differentiation. I'm going to pull through the 1/2. I'm not going to pay attention to it just yet. And I'm going to do the power rule for differentiation, which says bring down the 4 and then drop the exponent by 1. Okay. So again, this is the power rule for differentiation. It's the reverse, right? And then all I have to do is do the arithmetic. You can see 1/2 of 4 is 2 x cubed. So what you want to notice is this value here that I got out of the differentiation is the same as this value up here. So I'm showing you that one process actually does undo the other. Okay. So one way to check an integration is to differentiate it back again and see that you get the integrand that you started with. Okay. Is it clear to everybody? Okay, everybody good with that? Is that clear? And again, I can't emphasize enough that integration, like derivatives, is very, very rule driven, okay? And what I need you to be able to do is either crank through the rules if you're going to use, do them all by hand. There are most apps out there like Symbolab, Wolfram Alpha, that will do antiderivatives for you. But what is the most important is to be able to apply the process. Remember, you're going to use antiderivatives when you start with rate functions or marginal functions, and you want to get a total function back again. And that's going to be the most important thing, is knowing when to apply integration or antiderivatives, okay? So let's go back to the notes, okay, and see what other rules we have there. Okay, I'm going to try screen sharing again. Okay, here's a special case of the power rule. Okay, you might have noticed the what happens, okay, when you've just got dx, okay? That's like saying you've got a 1 dx here. There's no variable there. But remember, you can think of 1 as being x to the 0. Remember, x to the 0 is 1. So if you just see the integral of dx, think of that as a 1, and then think of it as x to the 0. Then you can apply the power rule on it. Add 1 to the exponent. 0 plus 1 is 1. And then divide by the new exponent, 0 plus 1. Add your constant. You can see this will give you x to the first, which is x. Okay? So if you're ever confronted by the integral of just dx, just that little differential, okay, remember what you're actually taking the antiderivative of is x to the 0, and that's just going to give you x to the first over 1, or x. Okay, that's pretty simple, and that's great that it works that way. Okay. Again, if you've got any comments or questions, okay, please put them in the chat. I brought up the chat window so I can see that. Again, I can't scroll with the chat window there. Now, here's an interesting bunch of examples, okay? This is a constant multiple rule, and again, what it's saying is pull your constants through the integration sign. You might notice when I did it on the board, I just put my hand over the constant. What you can actually do is pull it right through the integral sign and just focus on the variable part, okay? So here's an example. Suppose I want to take the integral of 2v to the v cubed dv, okay? You can either put your hand over the 2 and just do what you have to do with v to the third, or you can pull it right through the integral sign, which really like puts it on the other side of the fence so it doesn't distract you. And then you can use the power rule here, okay? V to the 3 plus 1 divided by 3 plus 1, v to the 4th over 4, which would either be 1/2 v to the 4th or v over 2 plus c. Okay, so this is exactly like what we just did on the board. Okay, so again, nothing new here. There's a little bit of calculus right here, and all of the rest is simplifying with algebra. Another useful fact about integrating is it works just like differentiating. Remember, whenever you had a function that had multiple terms in it, you differentiated term by term. You're going to do the same thing with integration. When you've got an integral with multiple terms in it, you're going to integrate term by term. That's what this says. If you have a plus or a minus between different algebraic functions, you can integrate the first, then integrate the second. What's a function? An algebraic term. Okay, so here's an example. I want to point out something about notation here. Notice, okay, when they have the integral of 3z squared plus 5, they put that whole function in parentheses, okay, before they wrote dz. The reason for that is the dz applies to the entire function. It is not correct to write this without the parentheses, just so you know, okay? Because we want to make sure you realize that we're differentiating the whole function with respect to z. Okay, so here's how they do it. And remember, if you can do any of these steps in your head, you don't need to do all the rewriting. But I'm showing you every single step so it's clear. Okay? So we're going to take the antiderivative of the first term plus the antiderivative of the second term. All right, I'm pulling the constant 3 through here. And then I'm going to do the power rule on the z squared, where I'm adding 1 to this 2 and dividing by the exponent. So this first term gives me 3 times z cubed over 3. Let's look at the second term. I pull through the 5, and then I just have the integral of dz. Remember that one from the previous example? That's like saying the integral of 1 dz, or x to the 0 dz. Okay, so I'm going to add 1 to the exponent to get z to the first, divide by the new exponent 1, and that gives me z to the first over 1. Okay. Simplifying all this out, you can see these 3's are going to cancel and give me z cubed, and then this term gives me a 5z plus the constant of integration. Okay, everybody okay with this example where I'm using multiple rules together? Okay, everyone okay with okay, just give me a yes or a no, a shout out. Okay, good with the multiple rules. Okay, good. Here's an example where I have exponents that are going to be negative numbers. Okay, this is a little bit more complicated, but it's not anything you can't handle because you've already dealt with this when you did differentiation. Okay, take a look at what I'm starting with. I have 12 divided by z to the 5th minus 4 divided by z to the 4th. These are two separate terms, so I can integrate or take an antiderivative term by term. Notice when I split the terms up, I had to write a dz with each term. You can think of it as distributing to everything in the parentheses, okay? So again, it's important that you don't lose the dz's, otherwise what you're doing mathematically doesn't make sense, okay? Then I'm going to look at this and I'm going to say, wait a minute, this is a z in the denominator, so I can rewrite that z to the 5th in the denominator as z to the negative 5th in the numerator. This is going to make it a lot easier to use the power rule for integration. So notice, I haven't done any calculus yet. All I've done is a little bit of algebra, separating it term by term, and then I'm basically rewriting the z to the 5th in the denominator is z to the negative 5th, and the z to the 4th in the denominator here is z to the negative 4th. Okay, so that's something that's going to come back again and again in calculus, so it's something that's worth getting really familiar with. Okay, now I'm going to pull through the constants, so the 12 comes through the integral sign here, the 3 comes through the integral sign here, and now I'm in a position to use the power rule for integration on both of these. So I have z to the negative 5th. Now remember, I'm adding a 1, so the number is going to get less negative. Here's negative 5 plus 1. Okay. Then I have minus 3, and then I have z to the negative 4 plus 1 divided by negative 4 plus 1, and then add the constant of integration. This right here is the only calculus step that I'm doing. That's the only calculus step. Then all I have to do is simplify the arithmetic. Okay, so negative 5 plus 1 is negative 4. Same thing in the denominator. Okay, if you look at this one, I've got negative 4 plus 1 is negative 3. Same thing in the denominator. okay? So here's what I've got, okay, if you take a look. This was a 12 times z to the negative fourth divided by negative 4. I can divide out a negative 4 in both of them, okay? So if I divide out the negative 4 in the denominator becomes a 1. If I divide 12 by negative 4, it turns into negative 3. So this first term simplifies into negative 3z to the negative fourth. Okay, take a look over here. I have a negative 3 in the denominator, a negative 3 in the numerator. That gives me a positive 1, okay, when they divide out. Negative divided by negative is positive, and the numerator and denominator match, so I get a 1. Okay, so this becomes plus z to the minus 3 plus z. And then if you want to, you can rewrite without negative exponents. Just put these guys in the denominator with a positive exponent. This becomes minus 3 over z to the fourth plus 1 over z to the third plus c. Okay. So again, this example has a fair amount of algebra in it. Again, there's only one calculus step. Let me ask before we do some examples, okay, and ask any problems with this one. Okay, can I scroll to example, please? You mean up here, Mary? Okay, so that's what we're starting with. So do me a favor, okay, and in the chat, ask if you've got any questions about this example, okay? I'm just repeating the same rule over and over again, okay, the power rule for integration. But this one has a lot more algebra involved in order to make it work. So please, give you a minute, ask some questions in the chat. The first example. Okay, sorry, Mary. Go up here. This one. You have questions on it. Okay. I'm going to wait a minute for you to have some questions on the two examples, okay? And then we'll try some ourselves, okay? Again, what most students have two problems with integration, okay? So just so you're aware of where the pitfalls are. First problem they have is they're doing differentiation instead of integration, okay? So please be aware you're reversing the process. Don't differentiate, you're integrating. And the second thing people have problems with, just like differentiation, is with the algebra. So again, it's a good idea to take a look at rules for exponents and all that stuff if you're still a little shaky. So I'm going to stop sharing this screen and go back to the whiteboard. Okay, so you can try some examples like this. Okay, so let me stop sharing. All right, and here we are with the whiteboard. Let me put up I'll put up one example and we'll work it together, okay? So I need you to find the antiderivative. Okay, so give me a minute. Okay, and I got my dx here. Okay, so everybody read that. Basically, I have the integral of 3x squared minus 7x plus 3 plus the square root of x dx. Okay, so give this a shot. Okay, I'll give you a minute to work on it and type your answer in as best as you can into the chat when you get it. Again, remember to use the caret sign for an exponent. If you want to show a square root, put your quantity in parentheses and use up arrow 1/2, okay? Give it a try and we'll work it together in a minute. Anybody stuck anywhere? I'm expecting a lot of people to get stuck with the square root of x, but you should be okay with the other terms. Okay, so don't be anxious if the square root of x is giving you trouble. Remember, rewrite it as x to the 1/2 before you start. It'll take maybe another 30 seconds or so to work on this. Okay, and then I'll work it out for you. But please actually give it a shot if you can. Okay, we have one answer. Okay. And again, let's take a look at it. I think you've got part of it right, Mary. Let's just take a look at it. Again, this is a lot to do at once. Okay, so let's just focus on it term by term. Okay, I know some of the rest of you are still working on it, but let's try to stay together here. Okay. First thing I'm going to realize is I could separate this out and work on it term by term. And again, you don't need to write this out like this, okay? This is just, I'm showing you what's happening. And I'm going to write the square root of x as x to the 1/2. Okay, so I've separated it out term by term. And again, you don't have to write it like this. You just have to remember integrate term by term. I'm going to pull through the constants. Okay, there was no constant to pull through on the last term. Everybody all right with it so far? Okay, everybody able to see it? Okay, good. All right, now I'm going to focus on actually doing the calculus part, which is with the power rule here. Okay, I've got the 3 out here. I'm going to add 1 to the exponent. Makes it a 3. And I'm going to put it over the new exponent. So this becomes x cubed over 3. Okay, over here, pull through the 7. The exponent on my x right now is a 1. So I'm going to add 1 to it. Okay, and write it over the new exponent. So that becomes x squared over 2. Here I have my, and this is just the integral of dx. Remember that one? That's like saying I have the integral of x to the 0. I'm going to add 1 to it, and that's going to give me x to the first, okay, which again will give me x to the first over 1. So that just becomes x. And over here, here's the complicated one. Okay, I'm going to work this out in a little bit of steps. I have x to the 1/2 plus 1 over 1/2 plus 1. Okay. And again, feel free to use your calculator if this is too complicated to just do, in your head. Okay, so I'm going to put a little blue line over here. 1/2 plus 1 is 1/2 plus 2/2, or 3/2. This becomes x to 3/2 over 3/2. Okay. And again, feel free to use your calculator to simplify any of the fractions like that. Okay. So let's go through and do this term by term. Here the 3's cancel out, and my first term is x cubed. And yes, I know there's a plus c over here. There's nothing I can simplify, so this is 7/2 x squared. Here's plus 3x. Now take a look at this term over here. This is our last term. We have a 3/2 that we're dividing by. Okay, we don't like complex fractions like this in algebraic expressions. So I kind of want to get rid of the fraction in the denominator. And again, what you have to remember is dividing by 3/2 is the same as multiplying by 2/3. So this becomes 2/3 x. Okay. So my final answer, let's see. My final answer is x cubed minus 7/2 x squared plus 3x plus 2/3 x to the 3/2 plus c. Okay, so again, take a look at that, and I'm going to ask any questions before we move on. Okay. If you could just give me a shout out. Any questions, yes or no? Okay, you can ask questions about algebra as well as calculus. All righty, I'm getting 4 no's. How about the rest of you? There's 9 of you on the call. Okay. All righty. Well, I think then we're ready to move on. Okay, so we'll take a look at other types besides just the power rule for integration. Remember, this is what we're going to use polynomial functions, but there's, as you know, there's lots of other types of functions out there. So we're going to move on to the other types of functions. Okay, so get back here and I will share my screen again. Okay, so let's take a look at exponential functions next. All right, so I'm sharing my screen and we'll go back to my notes. All right, now we're talking here about exponential functions where we have a base that's a. Remember, a can either be a number like 2, or it can be a number like e. Okay, remember, e is a number, it's not a variable. Okay, it's about 2.7. It's a special base. It's called the natural exponential base. So a is greater than 0, and it's not equal to 1. Well, if a is 0, raising it to any power isn't going to do anything. You're still going to have 0. And if a is 1, nothing interesting happens because 1 to any power is still 1. So that's why we're excluding these bases. Okay? So let's say I have the integral of some exponential base. Okay? And here's the exponent. It's a constant multiple times the variable. Okay? So an example of this would be 2 to the 7x, right? Or e to the 2x. Okay, those would be examples of the exponential functions we're talking about. So the way you take the integral of these is you write the exponential function in the numerator, then you divide by the derivative of your exponent and ln of the base, okay? You might remember when we took derivatives of exponential functions, we had the exponential function times ln of the base times the derivative of the exponent. The only difference here is because we're reversing the operation. We have the exponential base, but we're dividing by the derivative of the exponent and ln of the base, okay? So you see the parallels with taking a derivative of an exponential. Okay? We're adding the constant of integration. We're also saying our multiple up here, k, is not 0 because, well, a to the 0 is just 1, and that's not interesting either. Okay, so that's what all of these not equal things mean. Let's look at some examples. Okay, so here's the overall pattern I'm showing you. The integral of some base to a constant times x is the given function up here, which is a to the kx, constant from the exponent, which you can think of as the derivative of the exponent, okay? And then ln of the base here. That's the pattern. Okay, a can also be e. I said that already. So let's take a look at an example. Here's 2 to the negative 5x. In this example, 2 is my a, it's my base. Negative 5 is the k value, okay? So I would put this entire exponential 2 to the negative 5x in the numerator. I would put the k value, negative 5, down here and multiply that by ln of the base. So I have ln2. Add the constant of integration. So again, the pattern is really, really simple. Again, You're always going to be able to have an integration cheat sheet. You don't need to memorize these patterns. Okay, you just need to be able to look at something that's exponential and realize, hey, it matches this pattern, given function on top, constant from the exponent times ln to the base on the bottom, and I'm done. Here's an example with e. Okay, I have e to the 9t dt. So I'm going to put the entire exponential in the numerator, e to the 9t. I'm going to divide by the thing multiplying t in the exponent, that's the 9. This is my k value. And then ln of the base, which is e, and you must remember ln of e is 1, okay, plus c. So I get e to the 9t over 9. Integrating exponentials that have e as the base turn out to be really simple because you're going to get like a repeated pattern like this. You can see this has no ln in it, so it's pretty simple to deal with. Let's look at a messier example because, again, it's the basic concept over and over again. The only thing that gets more complicated is the algebra. Okay, so let's take a look. Here's example C. Here I have 3e to the 5/4 u du. Okay, here my exponential is really e to the 5/4 u. Okay, this 3 is a constant, so I'm just going to pull it through. It's a coefficient, pull it right through, and focus on the exponential part. Okay, so my k is 5/4. Okay, my base is e. So I'm going to put e to the 5/4 u on top. Here's k in the denominator. ln of e is a 1. Okay, so all I'm going to have in the denominator is 5/4 times 1. And remember, if I'm dividing by 5/4, that's the same as multiplying by 4/5. Okay, this 3 is the original coefficient. Okay, so I have 4/5 times 3 e to the 5/4. And the 4 and the 3 in the numerator multiply to give me 12 e to the 5/4 u over 5. Okay, so tell me, what do you think of this one? Is this one making sense? I'm going to open the chat so I can see your responses. Are these examples clear? Any questions? Could you back up to the top of the page for a little? Sure. Is that good? I really wish I could see the chat at the same time without covering the page. Okay, I guess you can see it okay. A little more up. This one. How's that? Anybody, any questions so far? I'll hang here for a while. And if you would just do me the favor of saying, yes, it's clear, no, it's not, that would be helpful. I realize you're not going to get good at this till you do some examples, so we're going to do that next. Okay. Okay, can you go to the last example, okay? Example C, this one. Okay, how's that? And please ask if you've got a question. I'll leave it up for a minute. Okay. Are we ready to try a few of these? Okay. Is it okay if I stop sharing my screen? Do you have what you need? Okay. Okay, let's try a few examples then of exponentials. Okay, so here's the whiteboard again. All right, so you're going to find the antiderivatives of these exponentials. Okay, here's the first one. All right, and here's the second one. Okay. So again, I'm assuming everybody can see those. First one is the integral of 5 times 2 to the 3x. Second one is 8 times e to the negative 2x. Okay, so I'll leave those up there for a while. I'll see how you do. Again, if you get an answer, type it in the chat the best as you can and use calculator notation. Okay. If you have any questions while you're working, just type those in the chat as well. I'm watching the chat as you're working. Okay, folks, I know you're probably still working on these, but we're kind of running out of time. I want to make sure I show you one last thing before we end. So let's work these together, okay? And you can ask me any questions as I go through them, okay? Oh, good, we've got an answer. Yeah, that's great. That's excellent, Yesenia. Thank you. Okay, so let's see how we get that answer for the first one. Okay, and then we'll work on the second one. Again, I apologize if you're still working. It's just kind of hard in this environment to see where people are and where they're stuck or where they might have questions. So let's work together. All right, here is my first function. Okay, this 5 is a coefficient, and the actual exponential is 2 to the 3x. Again, I know that because I have the 2 in parentheses, and that's what's being raised to the power. So I'm going to pull the 5 through the integration sign, and then I have 2, 3x dx. Here's my exponential. I'm going to use that pattern that I showed you. Okay, here's the 5 out here. Pattern says you have a fraction bar. The original exponential 2 to the 3x goes on top. And again, I don't really need the parentheses anymore. They were pretty much showing me that 5 is multiplying that exponential. So once I get the 5 out of the way by putting it outside the integration sign, I don't need the parentheses anymore. Okay, so I have 2 to the 3x, that's the exponential. And then downstairs, I have this constant up here in the denominator. And then I'm going to multiply that by ln of the base. The base is a 2. Okay, add the constant of integration. Okay, and then let's see if we can do any simplifying. Okay, I have a 5 in the numerator times this original exponential. I have a 3 in the denominator and an ln2 in the denominator. None of that stuff cancels out. Okay, you can't cancel out these 2's because one of them's an exponential base and one is an argument to log. They're not coefficients out in front. Remember, you can only divide out or cancel out factors, things that are multiplying your quantities. Okay, so this final answer is 5 times. Again, I'm putting the parentheses back to show multiplying with the 5. Okay, so the first one is 5 times 2 to the 3x over 3 ln 2 plus c. Okay, anybody questions about that one? Any questions about the steps? Good. How about the rest of you? We got 9 people on the call. Okay, just chime in if you've got questions. Okay, let's look at the second example. Here I have the integral of 8 e to the negative 2x dx. Okay, the 8 I'm going to pull through the integral sign. So my actual exponential is e to the negative 2x dx. Okay, I'm going to use the same pattern for integrating an exponential. Draw the fraction bar. The original exponential goes in the numerator. The constant that's multiplying the x and the exponent goes in the denominator. And then you have ln of the base. I'm going to write ln e, okay, plus c. Okay, then we're going to do some algebra on it. Okay, the first thing you have to remember is ln e is a 1. So this factor is just going to disappear. I don't need to leave it there. So I have 8 divided by negative 2, right? And I can divide out a negative 2 from both of those. Negative 2 goes into negative 2 once. Negative 2 goes into 8 negative 4 times. Okay, so I have 4e to the negative 2x. This negative 2 canceled out, and ln of e is a 1, so all I have in the denominator is a 1. I don't need to write it. So this example gives me an answer of negative 4 e to the negative 2x plus c. Any questions on that one? Actually, any questions on both? Okay, are we good? Take a minute, look at the examples, see if you have questions before we move on. Okay, are we good? I have 3 no's so far. Remember, again, I'm going to be saving this video, so you will be able to go back. You don't have to watch the whole thing. You can slide to whatever part of it you need to see. Okay, you don't have to watch from beginning to end. Okay, well, if there's no questions on these, let's look at the last topic. Okay, so I'm going to go back to sharing my screen. All right, and here we are back in the notes again. All right, you might have noticed that when we first did the power rule, it said that your power on x could not be -1. Let's think for a minute why that is, okay? Basically, when you do power rule integration, you're going to add 1 to the exponent. Well, if the exponent's -1 and you add 1 to it, you're going to get a 0 as your exponent. And x to the 0 is 1. So you will have lost your variable. Okay, that's why the power rule doesn't work when the exponent is -1 on x. That's a special integral. Take a look over here. If I have x to the -1 dx, that's 1 over x. Okay, x to the -1 dx. It integrates as ln of x. Okay, special case. Don't leave out the absolute value bars, because you might remember from college algebra, you can't feed negative numbers to ln. Okay, they're not in the domain of ln. So the absolute value bars just ensure that what you're putting in as an argument to log is a positive number. So that's a special integral. And the last thing we're going to do here is an applied example. Okay, like what would we want to integrate? Why do we need to find antiderivatives? Okay, so here's a business example. Suppose a publishing company has found out the marginal cost, keyword marginal cost means it's a derivative, at a level of production of X thousand books is given by this function. They're also doing you the favor of putting the prime here. Okay, so you know this is a marginal cost function, C prime. Okay. What they want to know is, they say the fixed cost, that means before the first book is produced, is $25,000. Okay. Find the cost function C of X. Okay. Fixed cost means $25,000 is what you're going to have to spend before you produce even 1 book. So it's the value of C of X when X is 0. This is important. This is going to help us figure out what the integration constant is later on. But again, it's important to realize this is a cost value, C of X, not C prime, C of X, and it's the cost value when X is 0. Okay, so let's scroll down, see what else. So marginal means you have a rate of change. C prime of X is a derivative. So what we can do is integrate C prime to get a total cost function. First thing I'm going to do is rewrite C prime to make it easy to integrate with the power rule. So I'm going to change that square root of X in the denominator to negative X to the -1/2. Remember, 1/2 means square root, negative sign means it was downstairs. Okay. Now let's do the actual integration with the power rule. I'm going to pull the coefficient 50 through the integral sign. Then I'm going to add 1 to my exponent and put it over divided by the new exponent, okay? I'm using k as my integration constant here so I don't get mixed up with c for cost. You could call the integration constant any letter you want, and I'm just using k here because my function name is c, okay? But it's the same integration constant. All right, let's clean this up a little. Okay, I have a 50 on the outside. Negative 1/2 plus 1 whole is positive 1/2. Same thing in the denominator, okay? Dividing by 1/2 is the same as multiplying by 2. So 50 times 2 is 100. 100 x to the 1/2 plus k. This is the final antiderivative. Now they wanted a total cost function. So I can't leave k, I can't leave this ambiguous constant in there. I have to use the information they gave me to help figure out what k is. Okay, so I'm going to use that information about the fixed cost to figure out what k is. We know when we make 0 books, our cost is $25,000. That's fixed cost. This could be for equipment, it could be for plant maintenance, who knows what. So what I'm going to do is I'm going to plug in 25,000 for the C of X part, the cost, okay? And I'm going to plug in 0 for X, okay? And notice when I do that, the only variable that's left in the equation is the K that I don't know. All right, so let's figure out 0 to the 1/2 is 0. 0 to any power is 0. 0 times 100 is 0. So I'm left with K on the left side and 25,000 on the right side. So I've evaluated my integration constant. Now I actually have a total cost function that looks like this. Okay, for this particular example, this particular publisher, this function will generate the total cost of making and producing X thousand books. Okay. Is everybody all right with how I got here? Okay, are you okay with the total cost function? Okay with getting C of X? You understand the steps, including evaluating the integration constant? Again, I couldn't have done that if they didn't tell me what their fixed cost was. Okay. Okay, now that we built a model, we can use it to determine the cost of making 100,000 books. Now remember, you're measuring X in thousands, so you're not going to plug in 100,000, you're just going to plug in 100. X is scaled by 1,000. Okay? So I'm going to evaluate this function when X is 100, plug in 100 here. This 100 is the coefficient. This 100 is the value of X. Okay, so this is essentially taking the square root of 100, which is 10. 100 times 10 is 1,000, plus the 25,000 fixed costs. Okay, so this is the variable cost of producing 100 books. Okay, so I have a total cost of $26,000 to make 100,000 books. Okay, so again, one last call. Everybody okay with this one? Everybody okay with the application example? Please chime in, just shout yes or no. Okay, if you've got a no, be happy to look at any questions you have about it, okay? There are examples like this in your homework, okay? They're applied examples. And remember, what is important actually about all of this is this last example, being able to use the concept of integration to go from a marginal, from a rate of change back to a total function. Okay? So essentially, that's the part you want to really make sure you understand. I'm going to stop sharing my screen and go back to the main window. And before we sign off for today, I want to ask any questions on anything. And that is not just math. Do you have questions about the course in general? Do you have questions about school in general? Is there anything at all you want to ask before we sign off for today? Anybody have any questions at all? All right. Again, please make sure to check your Maricopa email for the WebEx meeting invitations. We're going to keep meeting at our regular time on Mondays and Thursdays for the foreseeable future. I haven't gotten any information as to how long we'll be doing this. But again, my goal is to make sure you can all complete this course successfully this semester. All right. So hang in there. If you've got any questions while you're doing homework, if you want to set up a face-to-face meeting one-on-one, just send me an email and let me know, okay? Otherwise, I will see you next Tuesday, and I hope you have a good weekend. Okay, feel free to drop off the meeting anytime you want.